cyclopentane molecule, as Bayer had predicted, it does give us a much more comfortable looking bond angle from a carbon to a carbon to a carbon. It gives us a bond angle of about 108 degrees. That does seem to be a bond angle which is close to the optional or optimal 109.4. This should suggest that there's no strain in the molecule. However, that figure has been calculated. I think my molecule is hiding the figure. That figure has been calculated. And it's been calculated as 27 kilojoules per mole strain energy. But the problem is, as we look at our flat cyclopentane molecule, look along one particular carbon-to-carbon bond, this flat cyclopentane molecule, as Bayer predicted, does give us bonding orbitals which are eclipsed behind each other. One CH bond after another CH bond on adjacent carbons. So with that entire carbon ring, let me show molecule from a different angle. So for every carbon-to-carbon bond, there's 4 kilojoules of torsional strain above the plane and below the plane. So 8, 16, 22, 16, 24, 32, 40. That implies 40 kilojoules of torsional strain. The strain energy is apparently only 27. So there's something else going on, which we'll see over the page. So remember that as that carbon ring gets bigger, although the carbon ring restricts rotation of the bonds, it doesn't stop it altogether. So we've got an increasing ability of the molecule to twist and contort. So how does the molecule get out of this fix and start to have less strain? So if you look at that ring, what actually happened is that the last carbon actually puckers up or pushes up, almost like closing the flap of an envelope. And it causes the confirmation to start to become more staggered. Looking along that carbon which has been puckered up, looking to one of its neighbours, either the left side or on the other side, those 3 carbons and their bonding orbitals, they're looking very much staggered to each other. And that reduces the strain energy of the entire molecule. But it's just a puckering on one side of the molecule. If we look at the back end of the envelope, away from that flap, so this is the carbon that we've puckered up, and there's its neighbours on either side. You look around the back of the molecule, we can see that those bonding orbitals are still eclipsed. So there is still some strain energy attached to this molecule. It amounts to about 24 kilojoules of strain energy. Strain energy around the back here, and some strain energy here and here. But we've certainly staggered the molecule around these front 3 carbons. So Bayer is mostly right here. But he was wrong when he said the molecule was flat, and he was wrong when he said the molecule was strain-free. It isn't entirely strain-free. Okay? Of course, we can say that the strain in this molecule is pretty much entirely torsional strain. It's not angle strain which is the problem. And with the cyclopropane and the cyclobutane, the lion's share of the strain problem was Bayer's angle strain theory. Here the strain problem is mainly torsional strain. So cyclohexane, when we burn cyclohexane, turns out that it is free of strain energy, as Bayer predicted, but not for the reason Bayer predicted. He said that the molecule was flat, and a molecule of cyclohexane is most definitely not flat. Now we have to think about something that we refer to as axial and equatorial hydrogen positions. Remember, Bayer said that cyclohexane was going to be flat. There's a big problem if the molecule is flat. That problem is, as we look around the ring, from one carbon to its neighbour through a Newman projection, we rotate it around, it would put those bonding electrons, those bonding orbitals, in an eclipse conformation, all the way around the ring. But we know this isn't true because we know that there is no strain energy from the heat of combustion of cyclohexane. So this is not the conformation of the molecule. And the clue to the design of the molecule is in the cyclopentane last example. As we look at the molecule, one end of the molecule puckers up to turn the adjacent carbons into a staggered conformation with their bonding orbitals. And on the other end, if that's carbon number 1, carbon number 4 on the other side of the molecule, it also puckers. But it predominantly puckers down in the opposite direction. We're looking at carbon 1, carbon number 4. One end puckers up, pushes up. The other end pushes down. So the other 4 carbons, 1, 2, 3, 4, they make up the 4 points of a plane. The 4 points for the molecule is actually flat. The last one is pushing up. And on the other end, the next one is pushing down. So you can actually set your model up. And the cyclohexane molecule will sit on 1, 2, 3 carbon to hydrogen bonds which are pointing straight up and down. So every second carbon will have a carbon to hydrogen bond which is pointing straight down, acting like a leg on a table. And if you turn the molecule over, then the other 3 carbons will form the 3 legs of that table. And what has that done to the conformation? Well, now as we look down any one particular carbon to carbon bond, all of the groups surrounding it are staggered. As we rotate the ring around, each time get me the president. I always want to say that with the right the other ones are too shy. So as we rotate that molecule around, every single carbon to carbon bond has bonding orbitals which are staggered to each other. Staggering wipes away all of our torsional strain. It explains why the molecule is strain-free. So Bayer was correct that the molecule is strain-free, but not for the reasons that Bayer thought. For 4 and 5, it's not about angle strain, it's about stopping or minimizing torsional strain, the strain between bonding orbitals and adjacent atoms. Okay. For any carbon to hydrogen bond which is pointing straight up or straight down, we call those hydrogens axial hydrogens. And every single carbon has one example of an axial hydrogen. But the axial hydrogens flip back and forth from being above the plane to being below the plane. Above, below, above. So they're switching back and forth from being above to being below. The second carbon, sorry, the second hydrogen bond, I should say, on each carbon, the second carbon to hydrogen bond is an equatorial hydrogen to carbon bond. Now they're not flat with the plane of the molecule. Well, the molecule isn't flat anyway because it's zigzagging back and forth on itself in a staggered conformation. But these equatorial hydrogens, they're pointing either slightly above or slightly below the generalized plane of the ring. And like the axials, they actually switch back and forth. And we put the two together to give a one cyclohexane molecule picture. So every single carbon has an axial and an equatorial. That's one good thing to lock in your mind. If the axial is pointing down, then the equatorial is slightly above the plane. And if the axial is pointing up, then the equatorial is pointing slightly below the plane. We are going to need some practice at drawing cyclohexane rings which have axial and equatorial hydrogens. And here's a trick to do it every single time. So you start off by drawing two parallel lines which are sloping to each other, but they're slightly skewed from each other as well. So they're perfect, well, as close as you can get to perfectly parallel, but one's slightly ahead of the other, by maybe a foot. And that gives you the 1, 2, 3, 4 points of the 4 carbons which are in the same plane to each other. Now for the first and fourth carbon, if the lines are sloping up at this end, then the last carbon is pointing down, because the molecule zigzags back and forth, up and down on itself. So try and pick somewhere reasonable, and then join those two atoms to that point. Then for the other side, with lines sloping down, if they're sloping down, then the last carbon must be up from that point. So as best as you can, make the last apex point sloping up. So as we move around the ring, we are constantly zigzagging up and down the molecule, up and around that cyclohexane ring. Okay? Now to add the axial and equatorial hydrogen to carbon bonds. At each apex point, if the apex is pointing up, then that's the position for an axial which is above the plane. So follow the way the ring is pointing. And if those apexes are converging in an up direction, then your axial at that carbon point is going to be up. And if the carbon bonds are converging down the page, then your axial is going to be pointing down on the molecule. Now all we have to do is add in the equatorials. Remember, from the axial, if the axial is down, then the equatorial is slightly above horizontal. That's one of the most difficult ones to draw, something like that. It's hard to get good perspective. And as the axial is up, then the equatorial is slightly down. So it's dipping down at that point. Oops. Okay. So following those basic rules, we get a pretty good looking two-dimensional aspect of a cyclohexane ring.